Okay, so we deal with specification tests, and I don't know how far I'm going to get today, but I'll start by laying out the principle, and the principle is pretty straightforward, but it's good to have that straight in your head, what exactly is going on. Then a very common test, the most common test for spatial autocorrelation, Moran-Xi, but now Moran-Xi in the context of regression residuals, which is not the same as Moran-Xi as a descriptive statistic. Then we get a little more technical and get into the initial discussion of maximum likelihood estimation and how that results in three different principles of testing. And then we focus on one that got a lot of attention in the 1990s, the Lagrange multiplier tests, because they avoided the cost of having to estimate the actual model. So early on, it was really difficult to estimate spatial models or also other ones. So these Lagrange multiplier tests, or also called Rao score tests, it's the same thing, were very appealing because you could carry them out with just least squares residuals. And there were actually very good guidances as to what the next step would be. And then because multiple misspecifications can happen at the same time, there is a refinement of these tests, which is referred to as robust tests, but it's in a very limited sense of what robust is. And this is often misinterpreted, that one thinks, oh, these tests are robust to whatever, heteroscedasticity, nonlinearity, you name it. No, it's a very narrow sense of robustness that I'm going to talk about. And then if we have time today, otherwise I'll do it next time on Wednesday, I'll talk about the empirical power, how these things actually work. And that's, again, where the simulations come into play. And we probably won't do those in the lab, but the notebook is there, and you can play with it if you want to. So what's the principle? The logic is that, as you recall, estimation, both in least squares and in two-stage least squares, is subject to what we call regularity conditions. These are assumptions that we make, and a lot of these are difficult to verify. So we just kind of make them. We say, okay, we have a correctly specified model, right? It's linear. The error terms are uncorrelated and have constant variance, all these kinds of things. But a lot of these kind of assumptions are just assumptions, and some of them are actually very unrealistic in empirical practice. For example, when you work with cross-sectional data, assuming that the variance is constant is very unrealistic, So heteroscedasticity is the rule. Spatial correlation, less so, but still, especially when you deal with aggregate spatial units like counties or census tracts or things of that nature, it's likely that you have spillovers, because the scale and the range of the process that you're modeling doesn't match the scale and the range of your observational units. As I talked about before, counties are not labor markets. Sometimes they are, often they're not. Census tracts are definitely not neighborhoods. So these kind of spillovers are kind of unavoidable with this kind of data, not so much maybe with individual microdata, but with anything that's spatially aggregate and administrative units, typically, it's often a problem. And so how do you know that it is a problem? And that is really what specification testing is about. And recall the historical context. In the day, the MO was to avoid estimating a spatial model. This has changed. It's changed drastically because with the new software, it's really easy to estimate even very complex models. So that kind of concern has moved a bit, has disappeared a bit. I think it's still important to know how these things work and what they do and what they don't do. But to a large extent, the critical nature of using this to guide what is called the specification search is actually less critical in practice because you can just estimate anything you want. And then you can take it from there and kind of work backwards and see, okay, how do these compare in terms of fit? Do the estimates of the coefficients make sense? How do I interpret these models and work that way rather than forward, which is this logic is a forward specification search, starting with a simple model and moving to a more complex model. Now, the key to understand is that all these assumptions, these regularity conditions, are about a mathematical abstract, which is the error term. We never observe the error term. It's just there to put the randomness into the regression model. Without the error term, there's no randomness. But we have residuals. And lucky for us, at least in the least squares context, there is a connection between the residuals and the error terms. Not a one-to-one connection, because then we'd be in business. We take the residuals and we would actually obtain the unobservable error terms, but that doesn't work. So we get something that is related to the error terms, but it's not the error terms. But that allows us to work with these as we say under the null hypothesis. Because under the null hypothesis, all the regularity conditions are satisfied. So we don't have to worry about autocorrelation. We don't have to worry about heteroscedasticity. Everything works as advertised. And what's the logic? The logic is, okay, if everything works as advertised, what would the distribution of this statistic be? Okay, let's say we find that it should be standard normal. So we compute the statistic for our residuals, and if this gives us a value that doesn't fit the standard normal at all, then we reject the null hypothesis. Then we say, there's no way, this doesn't make sense. If the null are all our assumptions held, then there's no way that we would observe a statistic with this value, right? So if it's standard normal and you compute a statistic and you get a value of 10, what are the chances that you get a standard normal with a value of 10? Practically nothing, right? And so then the typical type 1 error type of decision process, you decide for yourself, is this rare enough for me to reject the null? And rejecting the null means something's wrong with my set of assumptions. And so then the next step, which is not that easy, is to figure out what is wrong with my model, right? Is it the heteroscedasticity? Is it spatial correlation? Is it nonlinear? Am I missing some important variables that aren't in there? Or any combination of these? And that's the problem with specification testing, because a lot of different causes can lead to the null to be rejected. Okay. The null hypothesis, in this case, is always the same. It's the classic linear regression models, that is a linear regression model that is well behaved. In other words, the linear specification is correct. It's not nonlinear of any way, of any kind. And the error terms are well behaved. They have constant variance, sigma squared, and they're not correlated. So the error variance covariance matrix is this n by n square matrix, sigma squared I. I is an identity matrix, just all sigma squares on the diagonal. That's all there is. No nonlinearities. Everything is well behaved, and also no endogeneity. Remember when we talked about two-stage least squares and instrumental variables, there the problem was that one of our assumptions, namely that the signal and the noise were uncorrelated, didn't hold. And we had to do something about it. So that's, in the ideal world, none of these complications happen. And then a lot of things can go wrong. As I mentioned, we could have non-constant variance, that's heteroscedasticity. Or we could have Of course, that's what we're interested in, spatially correlated errors. Or we could have problems because the spatially lag dependent variable is important because there is spatial spillover, as we call it, substantive spatial autocorrelation, and we don't have it in the model. If you remember the simulations that we ran, we created a spatial lag dependent variable for the y. Then we ran a regression ignoring that, and we saw that the beta would move out from its original position and its distribution would get wider and wider, meaning larger and larger variance. And one problem is that multiple alternatives may be in place. We don't know what is actually going on. That's where simulations come into play, because you can actually mimic one alternative or any combination of alternatives. So what happens if you not only have autocorrelation, but you also have, say, nonlinearity? What does that do to your tests and to your estimation methods? It's always the same way. We compare what is called a constrained model and an unconstrained model. A constrained model is a model where something is set to 0. That's the constraint. It doesn't look like a constrained model because you don't actually see the constraint. It's just not there. So if you have a least square specification, like here, x beta plus the error term, there is no spatial lag, or there is no SLX term, because it's constrained to have its coefficient to be 0. So it disappears. Okay. And then the unconstrained model is the model that actually has the coefficient. And so let me show you some examples. So if you recall, we have these 1-parameter models, then we have the 2-parameter models, and so on. The 1-parameter model, the constraint for the lag model is that rho is 0. So if rho is 0, this first term drops out, and we have a standard regression. So the logic here is, under the null, the model is constrained, limited, to have a rho value of 0. That's the constraint. Under the alternative, rho is not 0. Unconstrained model always has a better fit than a constrained model because it has more parameters. Remember what we said about adjusted R-square. It's the same thing. So you have more parameters, you always have a better fit. How much better? That's a critical question. Is it worth it, right? And that will be one of the ways in which we can test this. And later on, we'll be estimating a spatial lag model, and then we'll have what is called an asymptotic t-test on the coefficient of rho, which is essentially a hypothesis test on whether this coefficient is 0. So under the null, it's 0, and we get an estimate, say 0.2. Is 0.2 different enough from 0? That is our question. Now, in this particular perspective, so that's backward. You estimate the lag model, and you test the significance of the spatial coefficient. Here we're moving in the other direction. We start with the least squares model, and based on the residuals of the least squares model, we're going to try to decide, is it a lag model? Or is it an error model? Same thing, same logic. Here the coefficient, we call it lambda. If lambda is 0, this term drops, and it's a classic standard least squares regression model. SLX, same thing. Is gamma 0, then this WX term drops out, and we have the standard regression. So each case is the same thing. The unconstrained model is one of the spatial models that we talked about before. So the 1-parameter models, lag, error, SLX. If it's constrained, then the spatial parameter becomes 0, and we're back with our standard classic regression model. Then the 2-parameter models, or higher order models is the SAR error model, where we have both a rho and a lambda. And now here we have two levels of constraints. One level of constraint is in a lag model is lambda 0, or in an error model is rho 0. And then another level of constraints are both 0. And if both are 0, then we're back with our least squares regression. So now we have the least squares regression, and we have two possible constraints to check out, not just one. And similarly, if we have spatial Durbin, we have rho and gamma. And again, if both rho and gamma are 0, we drop back into our standard regression. So that's the logic. It's a forward specification search. We start with the simplest of models, the standard least squares, and based on the residuals of that model, we check whether we can move forward in the direction of one or another spatial model. Okay. Then later on, we'll see the backward approach. We actually estimate the spatial model and then check whether the constraint rho equals 0, lambda equals 0, gamma equals 0 could hold, right? And to do that, you have to estimate the model. Right now, with what we're doing now, today, we don't have to estimate a spatial model, right? Just least squares with regression residuals. Okay, Moran's eye. So Moran's eye is probably the most used test for spatial autocorrelation. I have it here in matrix notation and applied to the residuals of the regression. So the residuals we can compute easily, and then we apply Moran's eye expression to these residuals. So this is the cross product of the residuals with their spatial lags, rescaled by the sum of the non-zero elements of the weights matrix. So you may say, well, why don't we rescale by n square? We don't, because a lot of the weights matrix is 0, and we don't want to count that. So we only count the elements of the weights matrix that are not 0. So S sub 0 is the sum of all the weights elements over both I and j. In the new denominator, we have the sum of squared residuals divided by the number of observations, which is an estimate of the variance of the error terms. It's a consistent estimate. It's not an unbiased estimate. An unbiased estimate would be divided by n minus k, by the degrees of freedom. Consistent is in the limit. In the limit, you don't need to correct for degrees of freedom because n is very large. It doesn't matter. And then you divide by n. Now, in most of our applications, the weights matrix will be row standardized, as we saw earlier. So for a row standardized weights matrix, the sum for any given row of all the j's will be 1. Right? It's row standardized such that the sum of the weights in a given row is 1, and there are n rows, so the double sum is n. For row standardized weights, therefore, this denominator in the numerator and this denominator in the denominator cancel out, and we get this expression. Two cross products of residuals, one of the residuals with their spatial lag in the numerator, and one just a sum of squared residuals in the denominator. Right? And those of you who've done some econometrics, assuming it was written matrix notation, which is maybe a strong assumption, might recognize this as a Durbin-Watson statistic. You know, the Durbin-Watson statistic is a statistic for time series correlation, serial correlation in the error terms. It's pretty standard in any regression output. Some people run a Durbin-Watson statistic on, I've seen this, I'm not making this up, on the US states sorted by alphabet. Is this a statistic for spatial correlation? No. The alphabetical order of states is not any kind of meaningful spatial relationship, right? But of course, you can do it. And if you run a cross-section in some packages, they will give you Durbin-Watson, even though it's not time series. Formally, it's the same as Durbin-Watson. And if you remember anything about Durbin-Watson, you know that's a pain in the neck to get significance for. They have these, in the old days, they had these tables with the bounds, with the lower and the upper bound for different size data sets. I mean, the upshot of this is it's not easy to figure out what is the distribution of this statistic under the null hypothesis. So what is it that we need? What is the goal here? We compute this statistic. It's easy. We have the residuals, we get their spatial lags, we get these two cross products, we take the ratio. We have a number, okay? What does that number mean? You have 2.5. What does that mean? Or you have 0.9. What does that mean? It means nothing unless you have some sense of what its average should be and what's its spread around that average should be when the null hypothesis holds. So when the null hypothesis holds, we can, if you're good at it, we can actually derive what these means and these variances and these distributions would be. That's what mathematical statistics does, right? We won't actually do this, but I'll give you a sense of how it works, okay? The point of departure is that you assume the error terms. Notice what I'm saying. You assume the error terms to be normally distributed with a constant variance. Okay? With that assumption, can we know something about these residuals? The answer is yes, because there's a connection between the error terms and the residuals. And it's this monster here, okay? So a residual, and I'm just going to go through this very quickly so you get a sense of how this works. Then later on, I'm going to skip all the formal derivations. We just go straight to the result. So this is a dependent variable. This is X, and this is the beta estimator. X prime X inverse, X prime Y. Y is here, Y is there. So we bring it out, identity matrix minus this monster, multiplied by Y. What is Y? In the population, X with the true beta plus the error term. Error term is unobserved. Okay? You work this out, you get rid of the X beta parts, and you have a matrix of all observables, X's, multiplied by the unobservable error term. So the residual, which we can measure, is a product of a matrix, which we can construct, times an error term, which we cannot. Right? If this matrix were non-singular, it's square. If this were non-singular, we'd be in business. We would say the error term is the inverse of M times U. U we have, M we can make. If there was an inverse of M, we'd be in business. Unfortunately, there isn't. M is singular. M is a very powerful matrix that pops up over and over again. It's what is called idempotent, which means that when you multiply it by itself, you get the same thing back. You know, that's not the same as being 1. 1 times 1 is 1 for an identity matrix, but this is like 4 times 4 would be 4 again, right? It's a very powerful property of a very special matrix. And it also means that it's symmetric, so it's the same as its transpose. And you can do all kinds of things with it, which we will exploit later. So this is the key. Because now, anytime we assume something for the error term, we know what this means for the residual. So if we construct something like Morane's eye, we just replace the residual by this, m times e, and then based on the properties of this error term, which we assume, we can say something about the properties of the statistic. That's how it works. Okay. So the relationship between these two allows us to derive, as it's called, the distribution of the test statistic under the null hypothesis. The null hypothesis being that the error terms are normally distributed with a constant variance and no correlation, right? So how does this work? And this is where it gets fun, right? I didn't spend a week going over matrix algebra, but this is what you need to manipulate this. So what's the sum of squared residuals? As I said, we replace u by m times e. So on this side, it's actually e prime m prime, but we said m prime and m is the same, and m times m is m, so there's only one m left, right? This looks like a matrix, but it isn't a matrix. Remember my trick? 1 by n, n by n, n by 1, we end up with 1 by 1. It's a scalar. Here's a common trick. If you've never seen this before, it looks like magic, but it's actually very intuitive. Because it is a scalar, the trace of that matrix expression, the trace is the sum of the diagonals, is the same as that expression. So because it is a scalar, you can replace this by the trace of this matrix expression. And then traces, if you don't know this, it looks like magic, but traces have properties that you can rotate the order. You know, you can move the first one to the last one, and then the next one to the last one. And the traces are always the same. So we move this around, we move this first one to the end. Now it's not a scalar anymore, but the trace is still the same. So now we have the trace of this complicated expression, and we have this expectation operator, but only this part is random. And we know what it is, because we assumed the variance to be sigma squared I. So we have sigma squared and the trace of m. And as it turns out, again, I don't want to go there, but the trace of m is exactly the number of degrees of freedom. In other words, we know that if our assumptions hold, then the sum of squared residuals is related to the true variance and this multiplier n minus k, which gives us a natural estimate for this unknown sigma squared, which is going to be the sum of squared residuals divided by the degrees of freedom. This is something you do in your sleep all the time, but maybe you don't realize where this comes from. This is where this comes from. Because this is nothing but, there's nothing spatial or special about this, right? This one is spatial, but it's the same idea. Again, it's a scalar, so you can take the trace. It's a little more complicated, but you exploit this idempotent property, so all these transposes, they all disappear, and all these multiples, in the end, there's just one left. And now we have the trace of the weights matrix time this matrix. So these both are n by n matrices, right? And so now we're in business. We can do this for all the pieces and then figure out what are the mean and the variance of this construct using these kind of helpful expressions. And it becomes pretty monstrous pretty quickly. You see this thing here. This T is a bunch of traces involving all n by n matrices and powers of n by n matrices. So this is not easy to calculate, but also not impossible. They're just straight matrix products. There's nothing magic about them. There's a weight matrix, has a lot of zeros. This one is, M is not sparse, but W is sparse. So you can do some computational magic. And with some math that I don't go through, you can come up with what is the statistic on average and what is the variability around that average. And then you make another assumption. Then you assume that this statistic can be approximated by a normal distribution. And if you take out the mean and you rescale by the square root of the variance, which is the standard error, we have a standardized random variable, which under our assumption follows a standard normal distribution. So now we're in business. We have our residuals, we compute the statistic, we get the mean, we get the variance, we get a z value, and we look it up in a standard normal table. That's how it works. So a lot of assumptions, and unfortunately also a lot of math, but that's how you get there. The end result is that we don't really care what Moran's I is as a value. We do care what its corresponding standardized z value is. That z value we can compare to what it would be under a standard normal distribution, right? Moran's I doesn't mean anything to us unless we also know the mean and the variance. That's a big difference with other correlation coefficients. I stress this a lot when I talk about Moran's I in a purely exploratory context. People want to compare two Moran's I statistics. Unlike a regular classical correlation coefficient, you can't really do that unless you correct for differences in spatial weights, which affect the mean and the variance of these statistics. So same thing here. We don't even talk about it. We go straight to the z value and compare the z value to a standard normal. You can also, with some more magic and assumptions, get an exact finite sample distribution. That's actually not that useful in practice because these assumptions are too strict. They're typically not satisfied. Unlike what you sometimes see, permutation is never an option for residuals. And maybe you know why not. Because residuals are already correlated by construction. That M thing, you go from n error terms to n residuals, but you lose n minus k degrees of freedom, which means that there is a built-in correlation in any residual of any set of residuals in a standard regression. The Moran's I for residuals corrects for that. You know, all these m's in these expressions, they correct for that. So they give you the right impression. They don't make you conclude that things are correlated when they're not, purely because residuals are already correlated. So permutation is not an option. And as it turns out, in one of the notebooks, you can replicate this. The blue line is not an analytical standard normal, but I simulated, I believe, 1,000 standard normal random variates, and I draw its distribution. And then I compute Moran's I 1,000 times, and I draw its distribution, and these two track each other very closely. So it is a reasonable approximation, especially in the tails. Look how nice these tails track each other. And that's really what we typically deal with, is the tails of the distribution. Okay. Moran's I is great, but not so great. Okay. It's a great misspecification test. In other words, if you do not reject a null, then you can be pretty sure it's a pretty good model. However, if you do reject a null, you literally have no clue what may be going wrong. I mean, the natural reflex is to interpret this as spatial autocorrelation, and actually even more narrower as spatial error autocorrelation, but that's not correct. Moran's I has what we call power, means it can pick up spatial lag dependence, SLX dependence, heteroskedasticity, non-normality, non-linearity. It's magical. You name it, it will pick it up. Okay? Not with the same power for all, but it will pick it up. So if it doesn't pick anything up, that's great news. That means that the model is pretty solid. If it does pick up something, that's not so great news, because you have no clue what may be the problem. So then you're back to square one. The whole point was to use these indications, these diagnostics, to give you a sense of what may be wrong with your model. That's Moran's I. Moran's I is not provided by default in spreg because of all these matrix manipulations. You know, if you have very large data sets, that actually becomes very time consuming and creates some rounding errors, but it is an option. Instead, what we do compute is these Lagrange multiplier tests. Where does this come from? It comes from maximum likelihood estimation, and we haven't talked about that yet. But as a very classic and very old principle of estimation, you have something which corresponds to the joint probability of observing the data. We call that the likelihood. And the likelihood is a function of the parameters in the model. And you try to find the value of the parameters that gives you the highest probability that the observations come from that set of parameter values. That's kind of the logic of maximizing a likelihood function. It's essentially, you know, for example, you think your data come from a Poisson distribution. A Poisson is for counts, and the mean equals the variance. So you look at a phenomenon, you know, the classic Poisson distribution is people getting hit by horses in Prussia. That's one of the classic examples. So you have a bunch of samples of this, and you take the average, and you say, okay, that is my estimate that maximizes the distribution. But then you can actually compute what would be the joint distribution, right? And you can compute it. Say you have 5 incidents, and how many people got hit by a horse, right? And you compute what would be the probability of these 5 incidents be if the mean was 1? What would it be if the mean was 2? What would it be if the mean was 3? And you keep going, and each of these gives you a probability. And let's say it goes up first, and then it goes down. So you have found a maximum of that joint probability for a given value of the parameter. That's the logic of maximum likelihood. Now, maximum likelihood will give you estimates in a model, right? That's what we'll see next week. Then you have three ways of testing the constraint. It's always about constrained and unconstrained. So now we're in an unconstrained world. We estimate the parameter. How can we assess whether the constraint holds or not? There are three important principles. One is the value of the estimate. That's the one you all know as a t-test. You look for the significance of the coefficient. What does significance actually mean? It means whether the constraint that the coefficient is 0 holds. That is what you're checking. So that's the first principle, the value of the estimate. A second principle, we talked a little bit about that when we talked about adjusted R-square. It's about the fit of the model. If the fit of the model with the parameter and the fit of the model without the parameter are basically the same, then this parameter doesn't count, it's 0. So that's the second principle. And then the last one is a little technical, right? How do you optimize a function, maximize a function? You take the first partial derivative with respect to the thing that you're maximizing for. So in our context, that will be the first partial derivative of the likelihood function with respect to that parameter. Remember my example? You take the joint probability, you change the mean, it goes up, and then you reach a maximum, and then it goes down, then it goes down. How do we know that it's a maximum? The slope of the tangent is 0. Okay. So if we have an estimate, how do we know whether 0 is the maximum or not? We compute the slope at 0. If that slope at 0 is 0, then we have our maximum likelihood estimate. If that slope is not 0, then the question is, how non-zero is it? And that is the principle behind the Lagrange multiplier test, which is what they call it in econometrics. It's called Rao's score test in statistics. It's the same thing. Right? So the idea is, let me show you the picture. So the blue line is our likelihood function, which is really a joint probability. I mean, this is not strict statistics speak, but intuitively is the joint probability for the data as you change a parameter value. So as we change the parameter value, it goes up, it reaches a maximum, and then it goes down again. The parameter value down here, for which this maximum is reached, is called the maximum likelihood estimate. The first criterion I mentioned compares the value of this estimate to the 0 point. In other words, is this distance large enough to conclude that the estimate is different from 0? And how do we know whether or not it's large enough? We have to know something about its variability. In other words, we have to know its variance. And that's what you do in a t-test. A t-test uses the square root of the variance, but it's the same thing. It looks at the spread of the estimate. So, for example, let's say this is 0.54, right? If 0.54 has a variance of 0.1, can we conclude that 0.54 is different from 0? 0.1. Yeah, that's more than 5 standard errors away from 0. Right? But if 0.54 has a variance of 2, then we can't. So that's how the logic works. Second criterion, our maximum likelihood has a measure of fit, which is the likelihood, the joint probability, in other words. For our constraint, 0, we also have a measure of fit. What is the likelihood in a model where that coefficient is 0? That's this one. Our second criterion is then, how different are these two fits? Remember what we said about adjusted R-square? The R-square always goes up. Does it go up enough? Right? And the second test is called the likelihood ratio test. You may have heard this term before. That also requires the variance of this difference, which gets a little more complicated. And then the third test, at the maximum, the slope is flat. At the constraint, 0, the slope is not flat. How non-flat is it? So we need the variance of the score. It's called the score, the first partial derivative. So this is where things get a little difficult. We have 3 classic tests. The wall test, that's the one we're most familiar with, typically, asymptotic t-test. Likelihood ratio test is based on some notion of fit. Now, the likelihood is not actually fit, but it's a joint probability, and it's a proxy for fit. And then the Lagrange multiplier, or the score test, is the weirdest one, because it uses this concept of the score. That's why it's called Rao's score test, which is the first partial derivative of the log likelihood. And if this is all gobbledygook for you, first partial derivative is how you find the maximum of a function. So what we need to find is, what is the variability of this first partial derivative? And that turns out to be not that complicated. I mean, it's complicated, but not that difficult. In the limit, the 3 are the same. In finite samples, the t-test is always larger than the likelihood ratio test and then the Lagrange multiplier test. This has to be taken with a grain of salt. This holds if everything else holds. Remember, our assumption for the likelihood ratio is a distribution. We assume normality. If it's not normal, there's no reason for this to hold. If other things are not satisfied, there's no reason for this to hold. And as we'll see in the labs, it often doesn't hold. Okay. So here we get a little mathematical. The structure of the LM statistics is, it's always the same thing. So if you're comfortable with this, it's pretty straightforward. Unfortunately, in the spatial case, the math gets very complicated. The D is the score. That's the first partial derivative. If you have the likelihood function, you can, using matrix calculus, figure out what this should be, what this expression is. And then you have the likelihood function, you figure out this first partial derivative, and then you get its value imposing the constraint. So we'll do a spatial lag model. We get the likelihood function. We get the first partial derivative, which is a very complicated expression. And then we set rho to 0 in that expression. That is our score. And here, the middle part, that's a measure of variance. That's the inverse of the information matrix, Fisher information matrix, that's mathematical statistics. That's negative the expected value of the second order's partial derivative. So it gets really funky here. You really, if you want to do this yourself, you need to have knowledge of matrix calculus, which is not an obvious thing. The key here, which makes it both difficult and easy, the derivations, so all these partial derivatives, are based on the likelihood of the alternative. So the lag model likelihood or the error model likelihood. So you get this very complicated expression, but then it simplifies, sometimes greatly, by setting rho to 0 or setting lambda to 0 or setting gamma to 0. And to construct this test, you only need the OLS results. You don't need to actually estimate the lag model or the error model. So you estimate classic regression, you get the residuals, you get the estimates, the betas, you plug them into these complicated expressions, and you have your statistic. And the statistic is always chi-square. Chi-square, just as a reminder, is the square of a standard normal. That's a chi-square. Let's start with the first one, LM error. So recap, what will we need to do? We'll need to write out the likelihood function for the error model. We need to figure out the first partial derivative with respect to lambda, the second partial derivatives to construct this information matrix with respect to lambda. Then we set lambda to 0 in these expressions. And then we do this cross product of the score times the variance measure times the score again. This is row, this is a square, this is column. So the result is a single number, a scalar. And then we plug that into the chi-square distribution, and we're in business. So the no standard regression, the alternative, either a autoregressive or a moving average error. The score tests or the Lagrange multiplier tests are against what is called locally equivalent alternatives. So they're a little bit different from the null. This is all very subtle math stuff. If they're majorly different from the null, you're in trouble. Then it doesn't work. But if they're a little bit different from the null, then these things work. And they cannot tell the difference between autoregressive and moving average. That's a downside. So how do we go about this? I'm just going to put it in words. We partition the parameters. We do our likelihood for the error model. We have the partial derivatives, plug in lambda 0. We get this matrix with the second partial derivatives, plug in lambda 0, and here's what we get. The score is this monster, and after a little bit of work and plugging in the 0 value, we end up with the score being, does this look familiar or not? Okay, what's this? What's the numerator of Moran's eye? You can look back, or you should know this already. It's the same thing. This is exactly the same thing as the numerator of Moran's eye. The denominator of Moran's eye is u prime u divided by n. No, is u prime u. This is u prime u divided by n. So the score is directly related to Moran's eye. It's a scaling factor of n. Otherwise, it's exactly the same stuff. U prime WU divided by U prime U. That's Moran's eye. This score is U prime WU divided by U prime U divided by N. So that's N times Moran's eye. What? The N is in here. What?
It is sigma squared.
Sigma squared is U prime U, the sum of squared residuals, divided by N. It's not significant. Well, I mean, never use the term significant. Use something like meaningful or important or make sense, because significant then you're talking a hypothesis test, right? So this is not a test. This is just a score. It's interesting because it makes a direct connection between the score tests and Moran's eye. Information matrix, more traces, okay? You will see these trace expressions over and over. And they're, some of them are easy, some of them are not. Some of them are simply the sum of the squared weights. Others are a little more complicated. You have to actually work them out. Just call it T, and we're in business. Then the, remember, it's the score times this information matrix times the score again. So this Moran's eye is in here twice, scaled by n. And then we have this weird trace thing, which is only traces, nothing, no betas, no u's, nothing, just traces. So this is then the Lagrange multiplier test. You compute this. This is very easy. We've already done it. And then you divide it by this trace. This is not so easy. And this is big because they're all n by n. And here's the relationship between the two, right? I already talked about this. So if you work out the math, this gives you the connection between the two. So that's the error test. Then lag test, same approach, only more complicated. So we do again, we start with the likelihood function for the lag model. We get the score, we get the information matrix, we plug in row 0. For the SLX constraint, we get the likelihood function for the SLX model, score, information matrix, plugging gamma 0, and we get always the same expressions. So, as I said, this becomes pretty monstrous. The lag test, very similar structure, but now it's a cross product of the residuals and the spatially lag dependent variable. But otherwise, similar structure. The T is a little bit more complicated, but it's relatively straightforward to compute. And that's the lag test. Then the test for SLX, again, it's a monster. This has all these spatially lagged explanatory variables in here, and the error terms has, again, this time not sigma squared 1, but sigma squared h, where h is the number of explanatory variables less 1. Remember, there's no spatial lag of the constant term, so that's 1 less. You don't have to worry about this too much, it just calculates it for you. You do have to worry about interpreting it, which I get to in a little bit. So higher order gets even more complicated. So the SAR error model, we both lag an error, so now we get an even more complicated likelihood function. We get the scores, we get the information matrix, we plug in rho and lambda 0, and we get this test. Unlike what holds in standard econometrics or statistics, and this is a very interesting result, if you care for that kind of stuff. In standard Lagrange multiplier and score tests for higher order nested alternatives, the joint test is the sum of the marginal tests. What does that mean? That the joint test for rho and lambda should be the sum of the test for rho and the sum of the test for lambda. It is not. Okay, I'll get to that in a minute. So it's more complicated for spatial Durbin, it's even more complicated. So you see the part that has to do with the lag is the same as before. The part that has to do with the SLX term is with all these WX zeros. And this has K degrees of freedom. The H1s without the constant term, and then one more for raw. So now we have the joint test, and here too, the joint test is not the sum of the marginal ones. So what do we do with this? The natural tendency is to test the joint hypothesis first, and then to go to what is called the marginal ones. That's misleading. And we'll see later why. It's because the joint tests have really good power against one-directional alternatives. So it's a lag model, right? The lag test rejects the null. The joint lag error test also rejects the null. So your natural reflex would be, I need a model with lag and error. Not so. Right? It's the same in the spatial Durbin case. The joint test will tell you, oh, spatial Durbin, not necessarily. It could be just a lag model, or it could be just an SLX model. So the joint tests are actually, unlike what is the case in most of the rest of econometrics, they're actually not that useful. We can extend this, but then we get a little bit outside of the terrain of maximum likelihood and normality. But that's not a problem because we have central limit theorems. And remember what I said the other day, these central limit theorems give us normality on the route, on the way to the limit. In the limit, there's no normality. In the limit, we're right on target. But as we get closer to the limit, the variability of our estimator is such that it can be approximated by a normal distribution. That's what asymptotic normality means. That's what the central limit theorem gives you. So with these new sets of theorems, you can compute what is essentially a generalized Moran-Xi test. It has the same general shape, cross product of residuals and the spatial lag of the residuals, but then you can apply it to residuals from two-stage least squares. You can even apply it to residuals of a probit regression or a tobit regression, and so on. So I'm not going to dwell on this, but for example, you see, well, you probably don't, but this looks exactly the same as the LM error test, except now these are residuals from a two-stage least squares regression and not residuals from a ordinary least squares regression. So with the sophisticated mathematical statistics, you, in so many words, get the same results as under the idealized maximum likelihood framework, but without the maximum likelihood. Sometimes it's called pseudo-maximum or quasi-maximum likelihood. So it behaves like maximum likelihood, but it isn't maximum likelihood. And you get there through these various central limit theorems. So the bottom line is we can apply these same principles to residuals of all kinds of different models to test, without estimating the actual spatial model, whether there might be spatial effects. For the linear models, this is a non-issue, as I mentioned. For nonlinear models, like probit and count models and things like that, it still is an issue because the spatial versions of these models don't scale well. So for a very large number of observations, it's a computational challenge to get estimates in these models. We'll talk about that in the winter quarter, not in this one. Okay, I think I'm gonna keep it at that.